Okay, so let's start. Yeah, so before we start, thanks for inviting me, for giving this talk. I hope the audio is clear.
Yes, ma'am.
Okay. Yeah, so here is the plan. Yeah, so let me just quickly introduce myself. My name is Girija. I'm a faculty of computer science in BITS Pilani, Goa campus. So thanks to the coordinators for arranging this and inviting me. Okay. Yeah, so here is the plan for
Thank
today.
you.
Yeah, so I plan to talk about computational complexity, specifically the classes, the complexity classes, which are NP, P, and a few more. So just to get an idea, how many of you know about these complexity classes? Maybe not in detail, but have heard about P and P.
Is this kind of related to something like the big O notation or something?
Okay, yes, yes. Computational complexity is related, yes. Okay, I've heard of, okay, I also see some messages in the chat box. Okay, yeah, okay. So, yeah, I'll be defining these classes. So even if you don't know, that's fine. So that will be the first part. Then I will talk about the question P versus NP, which is also this question, right? Whether P and NP are equal or not. So that we don't know. I'll talk about that. But before I talk about that, I have to tell you what are these classes. So we'll start with the classes first, and we will also need a few more classes just to get the context clear. And then I'll talk about uh, NP completeness. In fact, we will also cover that here as one of the class, but I'll also talk about this specifically and its significance. Also, for P equal to NP or not, this question and its significance. We will look at these things. So this is what I plan to talk about today. Yeah, so at any point of time, if you think that I'm assuming something which you are not familiar with, please stop and we will go into those details first before moving ahead. I may not be able to see the chat immediately because I have to do the switch tab. So in case there is some pending question for long, then maybe you can just unmute and speak in case I fail to notice the chat message. Okay, so let's begin with the first part. Okay, so let me define two problems first, which we will be considering maybe in the first half of the talk today. So let's call one problem as prime and one more which I'll define later. So when I say problem, I mean a computational problem here. Okay, anything that where you are given some input, well-defined input, and you are asked to answer something, some output is expected out of that. And how do you get to the output? By doing a set of computational steps, mathematical steps, or you do some kind of arguments based on different mathematical or logical assumptions that you are known. So what I'll define is a very simple problem, prime. Let's say there is a positive integer, capital N. That is the input to the problem. And the question I'm asking or the output that I'm looking for is this answer to this question is N prime. Very simple problem. We'll start with some simple problems and we will dig into the complexity and the classes aspect, and then we will look at some possibly new problems. Okay, so the problem is very simple. It's clear, I think. The input is a positive integer n, capital N, and the question is n prime. So the output will be the answer to this question. So this is also called as a decision problem because, as you see, the question asked will have two possible answers, yes or no. So for most of the part, we will be looking at decision problems today. Maybe a few exceptions there I will mention when they are not decision problems. Okay, so this is one problem. I think everybody understood this problem. Please unmute and speak in case you have questions. And the other one is Sudoku. So everybody knows Sudoku,
Yes.
Yeah. Yes.
right? Okay. So I'm sure you must have seen this Sudoku, which is like 9 by 9, right? Typically, that is how it is. So you have 9 rows, 9 columns, and so on. We will generalize it. We will say that we have n rows and n columns instead of 9, 9. So I'm not defining Sudoku. I'm assuming you know that. But instead of a 9 by 9, which is a typical puzzle, we will look at n by n Sudoku. Okay. So what is the input here? It is n by n partially filled grid, right? So when I say n by n, I cannot just put 1 to 9 values. I have to put 1 to n values in every row, every column, and every subsquare. So I'm given a partially filled grid, which is of this dimension n by n. And typically when you solve this Sudoku puzzle, what you do is you fill in the values in the empty cell such that this rule is followed, right? Every row has exactly once, every digit appearing exactly once. Similarly for the columns, similarly for the subsquares. So yes, that is the solution usually. But here I want to formulate this as a decision problem. So instead of asking for the solution, I will ask it in a different way. I will say that, is there a valid solution? So what I mean by valid here is, so you are given this partially filled grid. You are supposed to fill in the values in the remaining, the empty cells. And a valid here means what are the rules of Sudoku, right? That every row should have each of these 1 to n numbers exactly once, every column and every subsquare. So, but I'm not asking for the solution here. I am formulating it in a different way. I want to,
Unique also.
yeah. Is there a question?
Does this mean that the solution has to be unique also?
No, I'm not talking about uniqueness. Does there exist or not? So when this puzzle is typically considered, we assume that there is a valid solution. It's just that we have to find it. But think of a partially filled grid which you cannot extend to a valid solution. The given configuration is such that there is no way to extend it to a valid solution. It is quite possible. So the question is asking whether that is possible or not, whether can you extend that to a valid solution or not. Uh, yeah, it may have multiple solutions, but at least one valid solution it should have. Okay. Yeah, so as I said, these are decision problems because the answer to this will be yes, no. Okay, so when I say decision problems, there are two possible answers. Yes, no, you can think about this true, false, something like that. So we'll be dealing with these two problems for quite a some time today. Okay, so now let's look at this concept of solving, which we usually do, versus verification. Okay. So if I give you this problem, prime, and if you're supposed to solve this, obviously you will come up, I mean, if I give you a particular n, let's say 27 or some n, and then the question is asked is n prime. So in order to solve it, obviously you will solve it thinking like, maybe let me try different factors, right? And whether do I find a factor or not, depending on that, you will answer this question. So that is the solving part. What I'm going to talk about now is verification. Okay, so what is a verification here? So imagine a situation where let's say I've given you one of these two problems, and your friend, there you are sitting next to each other, and you both got the same question here. Okay, the same value of n, or the same partially filled grid. I've given it to both of you, and you are solving it. You are trying to solve it, and at some point your friend comes to you, and he or she claims to you, let's assume that it's a Sudoku one, and he or she comes to you and says that See, I've solved the problem and the output is yes. What does that mean? The output is yes, meaning he or she is claiming that it has a valid solution. Okay. Now I'm saying that you don't solve it now. You verify her solution, his or her solution. So you see the difference. You are solving it so far, but now your friend comes to you and says that I have solved it and I have found a solution, and the answer to this question is yes, or it could be no also. But let's say it is yes. So somebody has made a claim about the solution, and now your job is not to solve the problem but to verify their claim. Okay, so let me write this down. So what is verification? It's verifying a claim. It could be a yes claim or a no claim instead of solving it. So is this distinction clear? We are going to look at specific cases of yes and no for both these problems. But is this distinction clear? Instead of solving it yourself, your focus now changes to verification. Somebody has given you a claim that, okay, I have solved this and the answer is yes. Now your job or your perspective is different now. Now you want to verify their claim. The claim may be true or false. That's a different question. But now your task is not to solve it. Now your task is to verify their claim. Okay, so is there any question about the distinction?
No.
Well, when we're solving the actual problem versus when we're verifying someone's claim about the problem, how could that possibly lead to two different methods? Like, effectively, we'd be doing the same thing, no? If we're
We'll
not
we'll
sure
talk
if the
about
claim is true or
yeah,
false.
we'll talk about that. We'll talk about that. If you have solved it, then possibly yes. But if you haven't solved it, then whether it will be same or not, we will talk about it.
I have
But
a
that's a very nice question. It's leading us to that. Yeah.
I have a doubt. Like the
Yes.
questions we are considering are like assume we prove that the answer is not no, then does it necessarily have to be yes?
Oh, yes, yes. Yeah. Decision question is framed in such a way that it will have exactly one of these two answers.
Okay.
Also had like
Yes.
one more question that
Yeah.
if you are, let's say, solving or and if you are, let's say, verifying, is there like a usual trend like which one becomes faster? Because let's say my friend has told me that, I claim that the answer is yes, but if verification would be faster, I would judge his claim, and if his claim turned out to be wrong, as mentioned just now, I would automatically know that the answer is yes. Is there like a general trend like which one is faster?
Yeah, so exactly what we are going to discuss, whether verification is faster, whether solving is faster, and how do we classify problems based on that. So maybe you should wait for a few minutes. Is that fine?
Yeah.
Also, this claim, this statement that you made, right? If we find out that the verification turned out to be false, the claim has to be false. Let's say the claim was yes, and you figured out that while verifying that it is a false claim, then we'll have to be careful whether we can directly, yeah, as far as definition is concerned, it has to be one of these answers, but it depends on how we are verifying. So let me take two examples, I mean the same two problems, and the yes no claim examples, and then possibly we'll revisit these questions. Is that fine?
Yes, yes, of course.
Okay, so let's start with prime and no claim. Okay, we will see why we are doing it this way. But yeah, let's start with a no claim. What does that mean? So this problem is being solved. You and your friend are solving separately, and then your friend comes to you and says that the answer to this is no. Okay, now your job is to verify whether this claim is true or false, whether the answer is really no or not. So if your friend tells you this, what should be the input that will help you to verify this claim?
Any factor?
Any factor? Everybody agrees? Any factor? Because the claim is no, right? N
Yes.
is not prime. Remember, the question is n prime? The answer is no. That means somebody is claiming that n is not prime. So, what makes you feel convinced about this, that n is not prime? Of course, any factor, right? So, let's say there is some d that your friend tells you, which is between this range. Of course, this is not needed. You can stop at root n. But let's say in this range, somebody whoever is claiming this no, They give you a value, a D. How will you verify once this is known to you?
Check and divide.
Check
Check
the
if
prime
divide.
modulo D.
Yeah.
Exactly. Simply check, right, whether D divides N. So sorry for the handwriting. I had to change the device and I'm not very comfortable with this device. So check whether D divides N, right? Correct? So if the claim is no, then and if this D is correctly given, then you will be able to verify the claim and say that yes, the claim is true, right? Now we will talk about the other question that had come up some minutes ago. That what if suppose three is a factor? Suppose three is the only factor. Okay, let's assume for the sake of it, let this three is the only factor, and if the claim says that five is the factor, still your verification will fail because three is the factor. Let's take it for simplicity. I mean, it might be like the number has to be four in that case. I mean, so three in that case, but let's stick to that. That some k is a factor and some k prime is not a factor, but still d happens to be k prime, so your verification will fail in that case. Okay, but that doesn't tell you anything whether the answer is true. The answer is yes. Okay, so d has to be correct. D has to support this claim. It cannot be some arbitrary number, right? D has to support this no claim. It has to be indeed a divisor, then only this verification will go through. So this D is called a certificate because it certifies that the claim is true. It is also called a witness, but yeah, certificate. Is this part clear?
Yes.
For example, if
Can
the
you
n
please
was
repeat?
6, yeah. So let's take an example. Suppose n is 6, okay? Then D has to be either what?
Two
2
or three.
or 3.
2 or 3, right? Right? So n is not prime. So the claim is correct. But suppose your friend gives you D as 4. Your verification will still fail. But that doesn't mean the claim is wrong. The claim is still true, right?
Okay, ma'am. Get it, ma'am. Thank
Right,
you, ma'am.
right. So what you somebody said, right, that if the verification fails, can we immediately conclude that the claim is false? So that is not true. The here we assume that this particular D in this case is, which is called certificate, is supporting the claim. So the D is true. D is correct one for that claim. Under that case, if we say that verification fails, then yes, definitely the claim is false. But if D is not supporting the claim, if D is given wrongly, then we cannot conclude that part. So that's what I wanted to highlight with this. Okay, so what do you think about this solving prime yourself? Okay, now think about a huge n, not like 6 or something, some huge n, and solving it yourself versus verifying somebody's claim that it's not a prime. Which one seems easier?
The
Verifying.
verification.
Verification if the claim is supportive.
Yes, yeah, we will assume that the claim is supportive. The certificate is like consistent with the claim. We will assume that. Then,
If
Well,
it's then
verifying should be
verification.
easier because in
Verify.
general to verify you can just solve for starters.
okay, if you can verify, you can solve, but that is only for the no case, right? What if n happens to be yes? I mean, n is a prime. What happens in that case?
No, like
Then somebody will.
what I'm saying is that verification should be easier because one method of verification is just solving the problem yourself.
I agree, but not just don't think about prime in this case. So in this case, I'm talking about a prime example as an example problem. But in general, can you claim this that if you can verify it, then you can also solve it?
Maybe not.
Maybe not, right? So in this case, also, it's not clear. What about prime with a yes claim? I was not planning to discuss that, but let's discuss it now. Prime with yes claim. If your friend comes to you and says that yes, it is prime, what should he or she give you so that you are convinced? What kind of certificate do you expect?
No divisor divides it.
The 2 to n minus 1, not any divisor should divide n.
Exactly, but then that is the solving, right? That is what you would also do
Yes,
to
that
solve
is
it.
just solving.
But here,
Yeah.
in case of no claim, solving and verification are different, distinctly different, right? For verification of no claim, you just need one divisor, that is enough. Assuming that it is indeed a certificate, it is consistent with the claim. But for solving, you would have done much more work because you have to go through that entire range 2 to n minus 1. Okay. Yeah. So, yeah, keep building some intuition. It's good that you are asking these questions, and we will be hopefully soon answering all of them once we proceed. These are all in connection with this question, actually. So, now let's look at Sudoku, but the yes claim. So, the yes claim for Sudoku. So this is the question. We are not looking for the solution, but we are looking for this answer. Is there a valid solution?
And the certificate he can give is a grid which is appropriately filled.
Okay. Yeah, so now you can start using these words. What is the certificate or what is the witness and what is the verification procedure? Both these things you have to tell me because that's what we did for this part, right? So let's like replicate it here. So what you are saying, the certificate is the, shall I say that complete configuration, field configuration?
Yes, and the verification process can be checking whether no number is repeated in a row, column, or a subsquare.
Okay. So let's write it down
Also
first.
checking that the numbers which were originally filled are still correctly filled.
Correct. Yeah. So in the verification, there are two steps, right? That the initial partial grid is not changed, right? Initial partially filled grid is intact. That has not been modified. And the n rows, I will just say n rows are valid. You mean what valid is? Every number should appear exactly once. Similarly, n columns are valid. And n subsquares are valid. Okay. Again, I'll ask you the same thing. Assuming that this complete configuration is consistent with the yes claim, he or she is not making any mistake when they give you this certificate. Let's assume that. Now, think about solving Sudoku versus verification. Do you see any relative difference? Like maybe one is easier,
Verification is much
Verification
easier.
should be much easier because verification you just check the rules of Sudoku and you check the squares. Solving you need
right?
to do a lot of deductive reasoning, perhaps, for example.
Exactly. So in general, in when you are solving it, if there are m empty squares, let's say, right? If there are m empty cells to begin with, then each one can take n possible digits, right? I mean, of course, you can make some observations and eliminate some combinations, but in general, n of them in each cell is possible. M many of them, right? So you already see that you have to consider roughly these many combinations. Of course, as I said, I mean, with some observations, you can eliminate some of them, but this looks like a much more tedious task than doing these three checks, which are very straightforward and much easier to do. Again, I'm not talking about what is easy here, what is tedious here. That we will formalize when we talk about the classes P and P and so on. But in some sense, we are talking about complexity. If you see, what is the complexity of doing this verification versus complexity of solving it? So we are slowly coming to the complexity part. But everybody agrees that at least for the two examples that we looked at, and specifically this combination, that Sudoku with a yes claim and prime with a no claim, it seems like verification is much more easier, much more straightforward than solving it.
Yes.
Yes.
Yes, ma'am.
Okay. Okay, so now we will try to formalize this using the complexity. But before that, let me. So, how many of you know about algorithms in general?
Some ideas.
Some ideas are
Okay, have
there.
you
Yes.
studied any algorithm as a part of any?
Yes, I've studied.
Yes, I
Some.
learned some. Like there was this Dijkstra's algorithm or something I remember, but I don't
Right?
remember it exactly.
Hmm.
And there was
Yeah,
also this,
yeah.
uh, I think binary search and min max, something like
Okay, you
that.
have learned binary search? Good.
Something like
I did,
minimum
yes, I
spanning
did learn
trees and
binary search, but
limbs.
I
Hmm.
feel like that is a very, very narrowed down approach to finding something. Like
Hmm.
The professor explained it by tearing the pages of a book in half so that he finds a particular page, but that
Right.
was one algorithm.
Correct. Correct. Yeah. Yes.
Heard of
Okay.
DFS and BFS if those count.
Okay. Okay.
Yes.
Then there's MST.
Traversals. Yes, minimum spanning tree, right? Dijkstra's is shortest path. Yes, so I think you have seen many graph algorithms, at least the preliminary ones. Good. So then I don't think I have to like start from the beginning. What is an algorithm and so on. Anyway, I'm not planning to do any formal definitions, but given any such problem, for instance, let's quickly see if you want to solve prime, what will be the algorithm? Algorithm is simply a sequence of well-defined steps. So what you will do is you will start with d equal to 2, 3, 4 up to n minus 1. Of course, you can optimize that, but let's say up to n minus 1. And every time you divide, you do this division, whether d divides n. If you find that d divides n, then you immediately solve the problem by saying no, n is not prime. Otherwise, you go to the next d till n minus 1. And if you don't find a factor, then you declare the answer to be yes. So this is algorithm. Okay, I'm going to give you a couple of more examples and algorithms for those without writing down any pseudocode or anything. What I plan to do is I'll take one example like this, and then a concrete example with particular values, and then we will just execute that algorithm on that example instead of me writing the algorithm itself. Okay, but in case it helps, I can also write it down formally. So let's see. So a very, very simple problem. In fact, given that you know about binary search and graph algorithms, the one that I'm going to present now is going to be a very simple computational problem for you. So it's actually, let's call it sum to zero. Okay, I'm just giving some name to the problem, sum to zero. So what is the input here? Remember, I am still in this realm of decision problems. Okay, so I'll define this problem also in similar way. So I'm given input as a list A, let's call it A, of n integers. Let's also assume that they are distinct. Okay, they can be positive, negative, zero, but they are distinct. The integers are not repeated basically, and n of them. And what I'm asking is there a pair of, when I say pair, it has to have two different elements, but let me anyway emphasize that I want a pair of distinct integers uh, whose sum is zero. Very simple question. Okay, so let's take one example. Let's say, let me know if the color or font is not clear, if the handwriting is not clear. So something like, let's say this. Okay, suppose this is my A. This is the list. So n is 7, sorry, n is 9 here. There are 9 elements in the list. Okay, so if I give you this input, and if this is the question, is there a pair of distinct integers whose sum is 0? What will be the answer?
Yes.
Yes. In
Yeah,
fact,
in
there are
fact, there are,
multiple of them.
yeah, there are two pairs, right? Are there more than two?
I think there's
No,
only
3
two.
No,
minus,
there are
yeah,
only two.
3 minus 3, 5 minus 5, right? So again, I'm not looking for a unique solution here. As long as there is a valid solution, you will say yes. So the answer to this will be yes. And this is a very simple problem for which I will tell you the algorithm, okay? And the reason here is I want to tell you about the complexity. Okay, so let's stick to the simpler problem so that we understand complexity, and then we will go to other a bit involved problems. Okay, so I think all of you know how to do this. Maybe one of you can tell me how will you do this, the algorithm for this.
I mean,
Very
if
simple.
I could just pick up like the positive number and try to search in the negative numbers if the mod values are similar. In that case, I can. I mean, if I could bifurcate the list into two parts with positive and negative integers, then it I think becomes easier.
Okay, you will
We could
bifurcate into two
also
parts. Yeah,
we
yeah,
could
go ahead, go
also
ahead.
sort the list and then check.
We could also sort the list. Yeah, we'll come to that approach. But let's say for now we are not allowed to sort. Then
Sorting would
There's
take a larger
there's the
time,
brute
wouldn't it?
force approach of just checking everything. We can't
yeah,
ignore
so
it.
Yeah, so I hear two replies. One is the brute force, and one is somebody said that will sorting take more time? Yeah, we'll come to that. That's why I said initially, let's not go to sorting. Let's try something else which doesn't require sorting. So, what will be the brute force?
So
I think
start
that
with the first number and then check it against all of the others, then the second and check it with all those to the right and so
Right.
on.
So let's stick to that right now. I'm sure there are better approaches, and we'll come to some of them. But just to tell about complexity in a bit formal way, let's stick to this approach so that we can analyze it nicely. So yeah, so this was the approach, right? So you start with. So this is your list. Let me write down the exact same list maybe. Again, as I said, I'm not going to write down the algorithm, but let's illustrate it on this example, and hopefully the steps should be clear. So this is the list. So as somebody said, sorry, I'm not able to figure out who is saying what because I have to keep element. And now that I know it is 5, in this part, I have to look for minus 5, right? So let's say I call the first element as, let's say f, right? Once I fix f, which is my first element as in that pair, the first element is 5. What should be the second element? It has to be minus 5. So I'll search for minus 5 in this, right? Now, this particular list is not that great because we stop here, right? As soon as we find it 5 and minus 5 are present, we stop here. So let me change this a little bit. Let me make it, let this be like that. Okay, something like this. So what do we do now? This is my first element in the pair. I look for minus 15 here in this entire part. I don't find minus 15. Okay, then I'll find this as a first pair. So sorry, as a first element in the pair. So this becomes my first element in the pair. Do I have to check with 15 again?
No.
No.
Because
No.
when f was 15, I already checked 15 13 pair, right? It doesn't matter whether it's 15 plus 13 or 13 plus 15. So I have to just look for this part, right? Then that also is not possible. Minus 13 is not present here. And then I go to the next element as my first of the pairs, first element of the pair. And then I have to search for minus 2 here. Then I find it here. And then I say yes, the pair is found. It may have multiple other pairs. That's okay. The answer is yes, because we have found at least one pair. So suppose the pair did not exist, then what we would have done? So this will also result in no, and then we'll go to the next number as f. We'll do the same thing. Again, the next number, same thing, and so on till the last number, till 40. 40 will be checked for minus 40 here, and for minus 5 there is nothing to check, right? So this red part is a hypothetical situation where the pair doesn't exist. Pair summing up to 0 doesn't exist, and then we would say no in this case. So this is a hypothetical situation. Just I am writing it down. So is this part clear? I mean, this is basically the algorithm. I'm not writing it explicitly, but this
You
is
must
what
give
we will do.
like a clever approach in chat
Yeah,
saying
yeah,
that
yeah.
store every number times minus one in a map.
Yes. So we will think about these approaches. Let's stick to this and let's complete the complexity analysis, and then we will move to the other approaches. So I'm sure that I mean you have already built the intuition about complexity, because otherwise you will not come up with cleverer approaches, right? Where you save time. But let's do it a little bit more formally for this particular approach. So first of all, I need to understand how big is my input size. How big is my input? Sorry. So we have n distinct integers. Okay. So let's say my input size here is n, because I have n distinct integers, a list containing n distinct integers. So if my input size is n, then how much work I am doing in this process?
I'm I'm searching n digits approximately for every digit I'm going through. I mean, I'm taking
It's
the work.
n choose 2, right?
N choose 2. Okay. How did you come
Worst
up
to
with n
worst
choose 2?
worst to
Like
worst
it's
you check
minus
every
1 plus and minus 2 plus all the way. So
Correct.
that's n choose 2.
well
Correct.
worst to worst you check every single pair. So you're choosing
Yes.
every pair
Yeah.
of
So there are
two.
at least two ways I see, and I think the both answers are correct. So one way is that you are checking pairs, right? A comma B pairs. Actually, it's not a sequence as such, A B, because that is same as B A as far as the sum is concerned. So we are looking for distinct pairs like this, right? where A, B and B are considered same. So can you say NC too many? Choose any two out of n, right? You
Yes.
have to consider all pairs. If you don't
Yeah.
consider any one of the pair and that happens to be the actual pair, then you are losing on the answer, right? So you have to consider exactly these many pairs. It may happen that you have to consider lesser number because, for instance, here you found it after not after NC2 pairs, you found it much earlier. But in case the answer is no, then you have to go through all NC2 pairs. Okay. So for now, for this talk, we will always say that this is like a max. You can do better. Even within this approach, you can do better. For example, in case of 2 minus 2, we stopped earlier. That's okay. But we will definitely not go beyond NC2 because only these many pairs are there to consider. So this is one way to look at it. The other way, as somebody else said, is in the first part, when 15 is fixed as f, we are looking at n minus 1 numbers. In the second part, we will be looking at n minus 2 numbers and so on. And in the last part, we will look at, so last time this will be my f and I look at just one number. So it is sum of 1 plus 2 plus 3 up to n minus 1, which is basically this, right? K equal to 1 to n minus 1, summation of k, which is a sum of first n natural numbers.
N into n minus 1 by 2.
Right. So if you see, both of these are going to be quadratic in n, something like n square. There will be constants. For example, you will have this half times that. Here also you will have that. In fact, this is exactly the same, right? NC2. If you split NC2, right?
Yeah, basically just disregarding the constants for the moment.
Yes, correct. We are disregarding the constants for the moment, but in general, we'll see that in complexity analysis, we will do that. And I'll also tell you the reason. Let me also read through the chat.
You're also disregarding the smaller, like minus n by 2. That's the.
Yes, yes, yeah, I'll come to that. Yes. Yeah, it's similar to sorting. Okay. Yeah, so we'll discuss one more approach, which is based on sorting. But yeah, so is this part clear? So it seems like we are going to need roughly n square, quadratic in n, many steps. So let's denote this as f of n, which is roughly n square right now. So why I'm saying roughly, why I'm ignoring minus 1 here and why I'm ignoring half here, I'll come to that. But this is like the first level of analysis for this approach. I'm sure there are better approaches, but let's look at this approach for now. Okay, so think about this. The goal of complexity here, the computational complexity, when I say complexity here, the goal of figuring this out for any algorithm is this. If my n increases, okay, so if n grows, typically we would like to find out something like when n tends to infinity, n becomes very huge. If n grows, how does f of n grow? In the sense, does f of n grow fast or slow? So when I say fast or slow, you need two f of n's, right? You need to compare two and say that this is fast and this is slow. Okay. So what we necessarily look at is the growth rate of f of n. So what is f of n here? F of n is this number of things that you are doing, number of steps that you have to do. Now, one thing to notice here is that you also need to keep counting these parts, right? That you are comparing this number with, let's say, this number. You are comparing this number with this number. So the actual comparison is also some work, right? Like comparing two numbers. Let's say this is your f and you are considering some s here, the second part of the pair. The comparing f and s themselves, that also takes some effort, some work, right? But we are kind of ignoring that because we will assume that these kind of basic operations, right, comparison or addition, they don't depend on the size of the list, right? What do they depend on? It depends on multiple things. Suppose I am doing this manually, like this. Here I did it manually with pen and paper, right? I mean, on the digital board, but something like pen and paper. then yes, some addition, some multiplication, division, comparison will take a different time. If you code this up, how many of you have done programming, some basic programming?
I have.
Maybe some
I
of you.
have done.
Yeah, so one way is like you just code this up, right? This input is given to you, you code this up in your favorite programming language and you run it. Now you may run it on maybe your smartphone, you may run it on some high end computer, you may run it on, deploy it on cloud, some lead code and all that, right? So where it is run, that will affect this, how fast multiplication is done, how fast comparison is done. But none of those things will be dependent on n. They will depend on the nature of the machine, the hardware, the CPU, or whether you are using machine or not, whether you are doing it manually with pen and paper. All that will have impact on this. How fast is your comparison? How fast is your multiplication? How fast is your division? Right? But none of these will depend on the input. Every time you do this multiplication on a supercomputer, it's going to take the same time. It doesn't change with respect to n. But what changes with respect to n is this f of n. Initially, here my n was 9. So I would get something like n to the power nc2 in this case, 9c2. But if this list becomes huge, if the list has 1000 numbers, then suddenly I get 1000 c2. Okay. So that is the reason we are just focusing on n. And because we are looking at growth rate, the constants don't matter. For example, if you have a square like this, a square function like this, let's say something like this. Sorry, it's a very bad drawing. Yeah. So something like this, a square function. What will a constant multiplier to this do? It will shift it entirely, right? The growth rate will not change. If you look at the growth rate of f of n, this is some quadratic function, parabolic kind of a curve. And then, so I'm assuming only positive ends because input size is going to be positive. You will not have negative ends in this context. What will happen if you multiply this by 2 or half or some constant? The entire curve will shift, but the
Scaled.
growth rate, sorry?
No, I said it will be scaled, but it will be
Yeah,
shifted
it will be
basically.
scaled. Entirely, it will be shifted, but the growth rate will not change. Now compare this with a linear function. So linear function will look like this, right? Sorry for it's not very scaled thing, but you can imagine this slope to be 1. So it's maybe I should draw it properly. Let's see with a proper straight line and all. Okay, so linear function is going to be like this, right? 45-degree line. And quadratic function is going to be like this. So you see the growth rate of quadratic function is much faster than a linear function. So when I say does n grow fast or slow, it's in comparison. So is n square better, is n better? So that's where the complexity comes into picture. So this particular algorithm, we said that it will roughly take quadratic many steps, which is a function of n. Of course, it may be something like n square. So in this particular case, we exactly have this, right? But this half doesn't matter because it's going to scale it up and down. And this doesn't matter because the highest order factor will dominate here. The highest order, in the sense, the highest degree in this polynomial. Okay,
It,
so
it's similar to like if we have like an infinitesimally small value, then when we square it in math, we just neglect it. Can we say
yes,
it like
yes,
that?
it's similar to that. Yes, yes. You can have a complicated looking function here, but what matters is the the largest growing term in that function. If it's a polynomial, then the highest degree term in that function. Also, like it could be something like 3n to the power 4 minus 5n cube and so on. So what matters is this, which is the highest growing among all of them. And also this 3 doesn't make any difference because it will only scale it up or down, but the growth rate will not change. So when we say complexity of an algorithm, again, there are different, somebody mentioned about big O notation. So yes, there are different ways to look at complexities, in the sense, can be upper bound this, can be lower bound this. But for now, somewhere I said that we will be only upper bounding this throughout. I don't remember where I said, but okay. So we'll be upper bounding it just for this talk. Okay, so we know that this algorithm, let's give it some name. Let's call it brute force itself. sorry, this is not the algorithm. This is the problem. This one, which I illustrated here, this is a brute force algorithm. So we can say that brute force is taking quadratic time. Brute force algorithms complexity is quadratic. Okay, so I'm being a bit sloppy here. This is not how we usually write. As somebody said, we will say something like order n square. But I don't want to go into the formal definitions. I just want to develop the intuition here that it seems to be taking n square, order of n square steps with neglecting these factors, constant and the lower order terms. Okay. Now we will come to other approaches, maybe one of them. But any questions so far? Anything I should explain again?
No, ma'am.
Okay, so let's talk about let's talk about another approach, and then maybe also binary search. Given that you have done that, maybe it's good enough. We'll see.
So like
So yeah.
if we have something which is taking floor of some function of n type thing,
Hmm.
then we can ignore the floor, kind of.
Kind of, yes. But I'm again being a bit sloppy here. It depends on whether we are upper bounding, lower bounding. Yes, but roughly we have to consider the highest, the term which has the highest growth, because all other things will be subsumed by that in some sense.
All right.
Okay, so I hope the share is there. Okay, yeah. So now let's do this approach where somebody suggested that we will do sorting. So have you learned sorting algorithms?
Yes.
A few.
No of them.
Okay, anybody remembers any specific?
Merge sort, quick sort.
Okay, so
There
but
was
do you
merge
remember the
sort.
complexities
I think O of n.
Yes.
of
N log n.
n log n? Okay, so
N
let's be
log n is
specific.
the
Yeah.
N log n is the best we can do for like non comparative sorts.
Yes, right. So let's be specific here. So I'll say sort the list using maybe merge sort. Let's be specific with respect to the
I'm not
algorithm
aware of the
because
terms, just to be clear. So like
okay. So we are not going into that. We will need that only for the complexity analysis. So somebody said that this will take n log n. So let's, yes, and this is true. Okay, so let's start with this. I mean, even if you don't know the merge sort, but I think sorting is clear, right? Sorting is you are arranging this list in the ascending order, or of course, descending order also is possible. Let's stick to this ascending part. So
yes, that is clear.
we'll look at this list again. We'll look at this list. Let me erase these things. And
We can do a two-pointer approach on this problem.
yeah, I'll come to that. Just a minute. So how we do merge sort, that is not explicitly relevant here, but given that that is one of the steps in our algorithm now, we have to consider its complexity explicitly. And as somebody said, it takes in log n time. Yeah, so theta in log n or we go in log n, will not go there, but in log n, roughly it takes in log n time. The highest dominating factor in that function is in log n. And then how do we search in that sorted list? So this is my original list. Now I'll do the sorting first, right? So let's say ascending, right? Oh, sorry, I have 5. Okay, negatives are done. And then 13, 15, 14. Okay, I hope I have not missed anything. Okay, so now once I have the sorted list, okay, so this to this will take some time. Okay, it's not free. We need to apply sorting algorithm, and we just said that it will take n log n time. So we have to consider this when we do the final analysis. Okay, we have to consider this step. And now how will we check for the pair? If I sort this first, how will I check for the pair?
You could start at a number, take that times -1 and do binary search on it.
Okay, yeah, we can do that. But is there a simpler approach? Maybe it's simpler.
I'm sorry,
Yeah,
I
so
missed
what
I
approach
missed
has
the
been
approach
suggested?
told by him. What was the approach?
So we will look for a number like -9, and then its complement 9 we will search in with the binary search, right?
Yeah.
Yeah. So you fix a
Can
number.
we do something like, since we now have it sorted in a particular method, so I know
Yeah.
that there are if I have a number, I need its additive inverse. So it must be, if I have a
Yes.
positive number, it must be negative. So I don't need to
Yes.
search the entire list. I can, whatever search I need to apply, I can apply it on a restricted area.
Okay, so one other approach is that because I know that this is -9, I just have to restrict my search to this area because this is positive. Is that what you are saying?
Yes.
Yeah, that can be done. But given that we are in this nice order, suppose I'll maybe start with first step. Suppose I look at the two extremes. What do they tell me? What is the sum right now?
The sum is
31.
31, which is
31,
positive.
right? We need 0, right? And we are getting positive sum. So what should we do
So
if
we
we want
should
to reach?
Move
decrement
the
the right
We
right
one.
should
one.
decrement.
We should decrement this.
Just keep going until we hit some sort of zero or negative value.
Negative, then we
If
go
we get
Okay.
positive.
zero, we are done. If we get negative, then we need to shift our
If
Okay.
we
focus
hit
to
negative,
another
then we
number.
shift the other side, perhaps.
Sure. So let's do that. So now we thought we found that this is 31. So we shifted this one. Now we are here. So what is the sum now?
Still positive.
6.
Still
6,
positive.
right? So it's still positive. So we'll still shift in the same direction towards the left. Now what is the sum?
4.
Yeah. Again, positive. So we shift. And now we
Okay.
have a negative value,
Now we
-7.
have a negative value. So we'll start switching from this side, right? Now. And finally we will hit this. Okay. So
Yes.
in this particular case, yeah, in this particular case, they also appear to be consecutive in the sorted list, but you can see that that is not always true, right? Like it's not always true that they are appearing next to each other. In this particular case, they are appearing next to each other. Okay. So now how many steps does this take, this approach take?
This will take like
Four.
at
I think
max
like
to
up to like
n.
roughly n steps.
Roughly n steps.
Yes,
Okay. That is one answer.
at
Is
max
there
n
any
is
other answer? At max n. Is there any other answer? Anything in the
Login.
chat? No. Login. Okay. Login is one more answer. Does anybody think that it will take more than n, something like quadratic in n?
No.
I mean,
Because the earlier we required quadratic because we couldn't miss a pair, and there are NC too many pairs. So it can possibly take those many. But now we are still looking at the pairs, but since we have this sorted order, every time we are reducing our problem size by one. Either from the left side we shrink it or from the right side we shrink it. So we will after n steps we will hit something like this. The both pointers will like collide, right, at after n steps, maximum n steps. So looks like a upper bound. You cannot have n square or something. N seems like fairly good enough. Everybody agrees with n that you cannot have more than n. We'll see log n, but so I
Yes.
can definitely say that this is something which is definitely upper bounded by n. Okay, the function is always upper bounded by n. Login can whoever said login, can you explain the logic? Why? What's the argument for login?
I think my since I just completely
Okay.
forgot that we disregard the factors, and it's not log n which we refer to, it's still n.
Yeah, it is still n. It's not exactly halved. Every time we will reduce it by one. So initially it is size n. Either we reduce it from left side or right side, it becomes n minus one. Again, either left side or right side shrinking, it becomes n minus two. In worst case, we'll have to do it for n many, where we will hit in this middle part. Both will collide. So log n is not correct. N is fine and n is good enough. So if we do sorting, then what is the total time then? We need n here and we also need n log n, right? Now you can see which is the dominating one here. N log n will
Log.
grow faster than n, so we will approximate it to n log n. But this is a better approach, right? Because n square will dominate n log n. Do you agree? What is n square? N square is n into n, right? And whereas this is n into log n. So because n dominates log n, you can see that n square is going to dominate n log n. So let's call this approach something sort and search. Sort then search. So earlier brute force took n square. Now this approach takes n log n. So it can happen that a fixed problem. What was the problem here? The problem was sum to zero,
Looking
right?
for a zero sum.
Yeah, sum to zero. So sum to zero problem has two different algorithms. I mean, I'm sure you can come up with other algorithms as well. In fact, you can think about this. Can you do this in better than in log n? Okay, think about that. But better than in log n as in something which grows slower than in log n and still gives you the answer. Okay, so we have two algorithms. So this is another algorithm. The first one was brute force. So when we consider a problem like this one, sum to zero. In general, a problem can have multiple algorithms. So we will see which one is the most efficient one. And that is the complexity for that problem. So here we will say that sum to zero, this is a problem. Okay, sum to zero is not an algorithm. It has two algorithms, sort, then search is one algorithm, and brute force is another algorithm. So sum to zero problem has complexity. We could have said n log n or we could have said n square, but as I said, we will look for the most efficient algorithm known for that problem. So as of now, in this particular discussion, today's discussion, we have n log n as the best possible, most efficient. Because n square grows much faster than n log n, and we would like to have something which is taking lesser time in terms of as a function of n. If n grows, then it should not grow too much. So here is where this comparison comes, whether it grows fast or slow. So we want something which doesn't have too much growth rate. Okay, so
Like,
this can happen in general for any problem. You can have just let me complete. Sorry, it can happen to any problem. You can have multiple algorithms, and we will look for the best known so far, and then that becomes the complexity. For this talk, we will consider it that way. Yes. What is the question?
I had a question. Like
Yes.
in the prime problem.
Prime problem. Yes.
So one way of solving was checking all numbers through 2 to n minus 1.
Yes.
And then another way we can check is from n minus 1 back to 2.
Yes.
So like intuitively it seems that the first approach should be better because the devices should be more denser towards the first, so we have a better chance of hitting a divisor towards the first,
Right.
as compared to like coming from n minus 1 to 0.
Yes.
So uh, is there a measure for this?
Yes, yeah, you can say that you want to start with the like starting from 2, you want to go up to n minus 1, right?
Yes.
First of all, think about this whether you still have to go till n minus 1.
I think his
No, like
intuition
we
boils
can
down
do
to going to
square
root
root
2.
10.
Root n, right? Okay, so now if you consider 2 to root n, 2 to root n, right? This is for prime, we are back to prime. So if we consider this, now your question is whether we should go this way and or this way, and whether does that come into picture in the complexity analysis, right?
Yes, right.
Yeah, it comes, yeah, it will come into the picture, but see, n is not fixed, n is a variable here. Okay,
Yes.
so you are saying that going from this side, you will, it's likely to have, here you will, you are likely to find like there's a large probability that you will find a factor here than in this part, right?
Yes.
Okay, so how will that affect complexity analysis? Can anybody comment on that? Will it affect?
In terms of the roughly stuff, perhaps not, because if it's prime, you still have to check everything.
Okay.
We're talking about the upper bound, so in general, it's going to be the same.
Exactly. So that's what I said, right? So there are ways to consider different bounds, like will it take at least n square? Will it take at most n square? But for this talk, we are sticking to at most. So suppose n is prime, then whether you go this way or this way, you will have to consider all the numbers in this range. So it will definitely not go beyond n steps. Oh, sorry, root n steps in this case. To be very specific, root n. Yeah, sorry, root n. Sorry, root n steps.
I forgot the
Like
name, the algorithm, but like what was it? I don't really remember, but like basically you eliminate each of those multiples of 2 first, and then you go on
Right.
3.
Ratastini sieve?
Yeah, the
like
Rattle is safe.
my question was
Yeah,
not
yeah,
Yeah.
sorry.
But that is to yeah, that is also there, but then you are given n here.
Is there like can we say that the time complexity of this is square root of n or is it still n?
No, the time complexity of this is a very different and tricky thing. Okay, so let me tell about this. So what is the input size? We are talking about input size every time, right? What is the input size first for the prime problem?
Square
It's a
root
bit
n.
tricky. Is it square root n?
Capital N, just
What
capital
is the
N.
what is the input? Input is n. So what is the size of that input? Remember, we are talking about size of the input. In this case, the size of the input is n, small n, because there were n elements in the list. Correct? So here you have to consider the input size of n. So n needs a specific number of digits to represent, right? Let's say n is some 10 digit number. Then 10 becomes the size of the input, which
Wouldn't it
is
be
roughly
log
log
2?
n. Yeah, log n. If we consider the binary representation, it will be log n. If we consider decimal representation, it will be log n to the base 10. But because the base, you can eliminate that in terms of considering constants, right? So you can consider log n in general. Now tell me, in terms of log n, how many steps do you need? Log n is your input size now. So this is my small n. Small is my small n. I'm kind of reserving for input size. Here we said this, right? The input size is small n here. So let's say what is small n for this problem. It is actually log n, because it's what is the size of the input? The input is n. It's a single number, but how many digits you need to represent that? So this is a bit tricky. Prime is I mean, many number theoretic problems have this kind of a tricky analysis. But now, given that I tell you that the input size is log n, you need root n steps. So what is root n as a function of log n?
Exponential in terms of it.
Yeah. So how will you write this? So this is n to the power half, right? This is n to the power half, and
Yes.
what
So
is 2 to the power
again,
log n? To the power log n. Let's assume it is base 2. Then to the power
okay,
log n is n.
N.
to the half.
Okay. So now this goes in the exponent, right? If you even if you simplify this, this goes in the exponent,
Yes.
right? So this is going to be an exponential in the way we looked at this problem. It is going to be exponential in input size. Okay, so prime is a bit tricky, but if we just follow the steps that we have been doing so far, what we get is a function which has the input size which is log n in the exponent. It is not something like n to the power 2, or it's not something like log n to the power 5 or 2 or something like that. It's not coming up to be polynomial. I'll talk about this. So does this mean that prime is not solvable in polynomial time? So I'll come to that question.
Ma'am,
Okay. Yeah.
So we would call the
like
complexity of this as root 2 to the small n.
Root to the log
Small
n.
n.
Okay, small n, yes. Yeah, but that's what, right? The input size goes in the exponent. So far, we have looked at the cases where it was not in the exponent.
I had a doubt.
Yeah, somebody else
So
also had a
so when I
question.
was asking that question, does the going from the left to right or right to left affect?
Hmm.
So I understood that the complexity remains the same, but say I had to perform this algorithm, and so the more practical choice would be to go from left to right. But their complexities are still the same. So how do I convey that?
Uh, yeah, so when we talk about complexity, so one thing, two things I already told you, that the constant factors don't matter and the lower order terms don't matter. That I already told you. Now there are also other two dimensions to this. So what is the best case input and what is the worst case input? And also the average case, obviously. But what is the best case input? The best case sorry, what will be the worst case input for prime? That n itself is a prime, right? Because you have to consider all factors in that case. That will be the
Yes.
worst time you spend. And the best case input will be something like even number, because at the first factor itself you find that, right?
Or
So
even like
what
a
you are
square
talking,
number if we are going from right to left.
yeah, even yeah, if we are going from right to left, then even a square number, right? But see, I mean, we are not talking about a randomized kind of an algorithm here. Once we say algorithm, we will use the same strategy, either go from 2 to root n or root n to n 2, for every n. We will not say that now that I know n is square, so let me start with root n. That is not possible, right? Because we don't know about n. We don't know whether it is a perfect square, whether it is a prime. We don't know that. So once we fix a strategy that we are always going from left to right, a 2 to root n, then we consider for this strategy what is the best case and what is the worst case. So in that sense, best case will be even number, because at first itself you find out that it's composite, it's not prime. And in the worst case, it's a prime number where you have to consider everything. So what you are talking about, how do you convey this, right? So we have to further do this analysis of best case running time versus worst case running time, which we are not doing right now, because we'll be even going into this polynomial versus exponential soon. So we will not consider these smaller things, like within, given that an algorithm is already polynomial, whether there is a best case to consider which will be more efficient and so on. We are just trying to bifurcate between polynomial versus non-polynomial for the context of this talk, where I want to define these classes. But you are right that how do I convey this? So you have to do this further analysis, fixing an algorithm, what is the best case, and then what is the complexity in that case. So even sorting algorithms will have such different behaviors in the best case, in the worst case, and so on.
Yes.
Okay, so right now I'm just focusing on polynomial versus not polynomial. Within polynomial, yes, you can do further analysis and say that in the best case it is in fact linear, and in the, let's say, in worst case it becomes quadratic, but still it remains polynomial. That is kind of our limit, polynomial and non-polynomial. So we'll come to that now. Okay, so we did a lot of things actually. So let's do a quick recap in case there is some question. We will do that, and then I'll define the complexity classes formally. So we looked at decision problems. Okay, so far we have only looked at decision problems, three of them: prime, Sudoku, and sum to zero. And we looked at this solving versus verification, right? So the task is, we don't care about solving in some sense. We are now with this task that verify somebody's claim, and that claim can be either a yes claim or a no claim. Now we are talking about, so when later on when we say algorithms, we will talk about algorithm for solving as well as algorithm for verification. Okay, so remember we discussed this, that does this verification procedure look simpler than solving it yourself? So we intuitively thought about the algorithm itself, right? What will I need to do to do this verification versus what will I need to do for the solving? So you implicitly thought about the algorithm itself for verification or for solving. So we will consider algorithms for both solving and verification. But here, just to highlight this difference, we focus just on verification part. And similarly for Sudoku, and for prime, no claim, and Sudoku yes claim. That's what we did. Then we moved to this third problem, and yeah, very very high level and very very informal notion of complexity. That is what we covered for two algorithms, and then we concluded that it has two algorithms, but the best one is n log n. And of course, you can think about this, whether you can further improve on this. Can you get something like n? Think about that offline. Uh, okay, so now let me move to this part of polynomial and exponential, which is the main theme of this, which will have this P versus NP. Will finally go there. So let me write down different types of functions. So n is our input size. So let's assume it for simplicity small n every time. Okay. So something like log n square log n, maybe n to the power half, yeah, root n, then n to the power 5 by 2, maybe n square, sorry, n to the power 5 by 4 log n, maybe something like log n to the power 5. Okay, I'm writing just some functions of n, and then here I'm writing a different type of functions. Hopefully we will see the difference clearly. Let's say something like 2 to the power n, n to the power root n, something like 2 to, let's say n square times 2 to the power n, 2 to the power log n, and so on. Let's say 5 to the power log n. Okay. So fundamental difference, as you see, is everywhere you will see n in the exponent in this part. Okay. Whereas here, no matter how complicated the function is, you will never see n in the exponent, right? I mean, you can think of many more such functions here as well as here. I'm just giving some functions here for simplicity. Uh, so what we tend to see here is that the complexity can fall in any of these categories, right? It can be something like this, or it can be something like this for a given problem. So exponential, as you know, this has like a huge growth, or it's like the very fastest growing functions. Like even these type of functions are even faster, but in general, whenever you see the exponent, n in the exponent, you know that it is much faster growing than any of these polynomial functions. And that is the basis of this p versus np. Not exactly this, the polynomial and exponential, but this is what makes all the difference in terms of finding out complexity and defining these classes and so on. So what we intend to have is something like this, and we will try to avoid this. Okay, so most of the algorithms research that happens is, given a new problem for which there is no algorithm, can you come up with an algorithm whose complexity is falls in this category, where you don't find this n at the input size at the exponent. Okay, so that is like even my work currently is looking at different problems which are not solved and trying to come up with a polynomial time algorithm for that problem. So that is one of the things. Now we will define the first class, which is P.
Before defining, I had a small doubt, ma'am.
Yeah, go
Is
ahead.
there anything between? I think that
Oh,
might have
yeah.
been part as well.
Yeah, is there anything between? Yes. So, there are things here. So, one example will be, let's say, this. So, this is called pseudo polynomial. Is this prime? Yeah. So, pseudo polynomial. So that is kind of in between these two. Yeah, there are other things as well, but I don't think even I have like very clear understanding about that. I don't work in this middle part too much, but yes, there are things here, and this one, for example, is called pseudo polynomial.
Ma'am, coming back to my doubt,
Yeah.
is there any problem, like we are making all these algorithms for problems, is there any problem in which like the researchers and everyone had to like come up with only an exponential problem, they had to suffice with it, and there should not be any polynomial, at least till modern research?
Yeah, yes, there are such problems. I'll tell you some examples in some time. We'll come to
Okay, ma'am.
that. Okay, so let me define the first class, P. So when I define these classes, these are classes of problems. So we have to keep this in mind. We are classifying the problems, not the algorithms. A problem can have multiple algorithms. We choose the best known so far, best in the sense the one with the slowest growing growth rate, and then based on that we will classify the problem. Also, when we say problems, we are for now we are just looking at decision problems, and we are also looking at solving verification both. So once I start defining the classes, it will be clear what aspect I'm looking at. Is it solving or is it verification? So class P is a set of problems that can be solved in polynomial time. Let me write it polytime. It means polynomial time in input size. So this polynomial has to be in the input size. We have been calling it lowercase n. So it's a set of problems that can be solved in polytime. I'll give you some examples that you already know. Merge sort, it's n log n, right? So this is an algorithm, right? Remember merge sort algorithm, right? So that means sorting problem can be done in polynomial time. So this goes to the class P. So everybody knows this, right? This is set membership. Sorting belongs to
Yes.
set P. So this class we will also say this is a set of problems, right? Set of problems. So sorting is the problem that goes to this P class because there is an algorithm merge sort which has this polynomial time. Again, it is not exactly polynomial, it's n log n, but you can upper bound it by n square, and that is a polynomial. For the purpose of this talk, we will just consider the upper bounds. It is definitely not needing exponential, something like 2 to the power n or something. Now you also know MST. I think somebody said MST, right? So that is a minimum spanning tree problem. So there is an algorithm for that, and that is also in P. Even if you don't remember the complexity right now, that's fine. But you can verify it later on. That is also in P. Dijkstra's algorithm. So again, this is an algorithm, so we will not classify this, but this is for the problem of shortest path. So the problem here is shortest path, and that is in P because Dijkstra's algorithm runs in polynomial time. So sorting, even binary search, somebody told about that also. Binary search. So that's an algorithm. It has complexity log n. So what it does is a searching in sorted array. Searching in sorted list, let me write. So if we are given a sorted list and a number to search or an element to search, then that searching can be achieved in log n. Therefore, this problem is also in P. Okay, so these are some of the things that you already know. We'll talk about other things. We will so what about prime now? Okay, so as of now, this is pseudo polynomial, as I said. But there is a result. There is another result. Okay, there is a result. There is another result, not the one that we have looked at, because that is not polynomial in the input size, as we said. But there is another result. I think it's called AKS algorithm. This is a short form of the three people who invented this. Um, so this one is Nitin Saxena, who is a faculty at IIT Kanpur right now. So there is another result that shows that prime is in P actually. So not the earlier one that we saw, but there is a result which shows that prime is in P. Okay, so some examples. I mean, of course, now you may think of multiple problems and you will have this question, are they in P? Yeah, so we'll defer those questions for now because I want to define other classes and then maybe we can look at more problems and think about
I had
them.
read about this algorithm. It
AKS?
has
Okay.
like a log of
Yeah, I read about it
some
somewhere.
base and
Yeah,
everything.
yeah, yeah. Yeah. Also, now that we are at the prime, let me also give this. Maybe you can think about this as a offline thing. So we looked at this combination prime and no certificate, no claim, and Sudoku with yes claim. So what about the other two combinations, right? Prime with yes and Sudoku with no. So you can think about that. And towards the end, like if you have enough time, I don't know, it's already 5:30. Let's see. If you have enough time, we will also discuss the other two claims, but we haven't covered that, right? So maybe you can think about them offline in case we don't get to cover it today. Uh, okay, so the point is this is the class NP and set of all problems that can be solved. Okay, we'll soon come to verification that can be solved in polynomial time. And here are some examples that you are aware of. Sorry. Okay. So now let me define the classes with respect to verification. So now we are switching to verification again. As we know, there are two types of verification: yes claim verification, no claim verification. Okay. So the set of problems for which I'm really sorry for bad handwriting. It's because of that sudden change in the device. A set of problems for which yes claims can be verified in polynomial time. Okay, so now here we are not talking about solving it, but verifying it. Also, when I say yes claims, we also assume that we have a consistent certificate. Okay, so let's stick to that assumption for now. So this class is called NP. So this is class NP. It's a set of all problems that for which you can verify the yes claim in polynomial time. And remember, we are completely sticking to decision problems here. So this NP class is well defined right now. Of course, P doesn't matter. I mean, it could be a decision or uh, the other type of problem, like find the solution in the Sudoku, the actual solution instead of yes no question. But for NP at least, right here, when we say verification, we are sticking to decision problems.
Aren't these two bijective?
Which two?
Yes and no.
Are you trying to
Like
say that if we have a polynomial time verification for yes, then then there is a polynomial time verification for no and vice versa?
no, like if there is a problem that is in yes that has that can be verified verified yes, then there's a problem that can be verified no.
Oh, okay. And what is that problem?
Just the not of that, like if there is.
Complement of that, right. So basically I can just say here, go back here and say that sudoku wait, where is sudoku? Yes, yeah, sudoku yes claim can be verified. So I can define something like here I can define sudoku as maybe some other problem. Let's say where is sudoku. I can define something like in sudoku, and then I ask a different question, right? Something like this. Is there no valid something like this? Are you saying
Yeah.
this way? Is there no valid solution, something like this? Okay, so
Yes.
what is your claim now? If sudoku suppose sudoku is in NP, then this problem will have the no verification done.
Yes.
Okay, does everybody see this, or is there any question?
I mean, I don't see it. I don't get it at first.
Okay, so I am redefining the problem first of all. Now I'm defining a new problem. Let's call it n sudoku. Okay, let me define it like co-sudoku, co for complement. Okay, so what is co-sudoku? I'm still given n by n partially filled grid, and instead of asking is there a valid solution, I'm asking is there no valid solution. So the answer to this will be yes when there is no valid solution, and answer to this will be no means there is a valid solution.
Okay.
If there is
So
a
this is
valid
what he was
solution,
talking about.
So now what he is saying is that if sudoku is in NP, can I say that for co-sudoku the same verification will work for the no part? So what does that mean?
Okay.
Co-sudoku is having no answer or a no claim. That means there is a valid solution, which is same as saying the sudoku has a valid solution, which is a yes verification for sudoku.
So it boils down to that first question of the class, that if I am having a prime, I'm given a certificate. If that certificate does not match, can I say that it is not a prime? In that case, it doesn't work. In this case, the complements do work, right?
No, I think in that case you were still sticking to the prime and just saying that if I get a verification of yes claim false, do I conclude that no is true? No is the answer. But here I have defined a different problem for Sudoku. So
Okay.
for which, okay, so if I just look at Sudoku problem, which grids will have yes answer? Those which have valid solution. Right? If I just
Yes.
look at Sudoku problem and I consider, let's say, 100 different grids which are all partially filled, out of them, out of those 100 grids, which will have a yes answer, those which have valid solution. So if there is a grid which has yes claim for Sudoku, does it automatically mean that it has no claim for co-Sudoku? Because that has a valid solution. So co-Sudoku's answer will be no in that case. Is there no valid solution? No, because there is a valid solution.
Okay, so just a complementary question to the original question.
Yes, yes. So what he is saying is there a bijection like this? If I am getting it correctly, right? Is that what you said? If I
Yes.
have a problem here for which yes verification can be done, then there will be because he said bijection, there will be a corresponding problem here for which the same verification will work for the no claim of that problem, right? So in fact that is true, and why I defined it like co-sudoku is because this class will be called sudoku. Sorry, this class will be called co-np. I'm sorry. So this is the set of problems for which no claims can be verified in polynomial time, and this class is co-np, complementary of np. So if a problem is in np, you can think of its complement. Okay, you can think of its complement. Okay, so now in fact let me complete this part and then maybe we'll come back to this question. So we know about prime, yes certificate, no certificate. We have looked at some combinations out of these four. Out of these four we have looked at two combinations. So we saw that sudoku no can be done, right? Sorry, sudoku yes can be done, right? That person gives you the certificate which is the entire filled in grid, and then you have to check all in columns, all in rows, and all in subsquares, and that checking that will take time polynomial in the size of grid, which is n square itself. So this can be done in polynomial time, right? Everybody agrees that Sudoku is in NP
Yes.
because its yes verification can be done in polynomial time. Now we looked at prime problem. We said that we looked at this claim, right? No claim. We said that a fraction, a factor d is required. So how big can d be? D cannot be more than n, right? So if n requires 10 digits, d also requires 10 digits, not more than that. Maybe lesser than 10 digits, but definitely not more than the size of the input n itself. So D size is bounded, the certificate is small enough, and what you are checking is just one division. And that division takes time, which is independent of the size of the input. So this also works, and therefore prime is in co-NP because its no verification can be done. But that doesn't say anything about this. Okay, if it is in NP, that immediately doesn't say whether Sudoku is in co-NP. What we said is the different problem in Sudoku. In Sudoku is a different, co-Sudoku, sorry. Co-Sudoku was a different problem. Just having membership in NP doesn't say anything about membership in co-NP or the other way around. This we haven't discussed, okay? Instead of writing question mark, I'll say we haven't discussed.
For primes, it is true.
Why? You mean for primes it is also in NP?
Yes.
Why?
We can check all the numbers.
Yeah, we can check all the numbers, but we said, right, that it is not polynomial, it is pseudo polynomial because the size of the number
Oh,
is
yeah,
log
yeah,
n.
yeah.
So with that it is not. I mean that reasoning is not correct, but your answer is correct that prime is in NP. We will come to that why it is in NP,
You said
but
there's
that
an
not because of
algorithm.
that reason.
Because of the
Exactly.
EPS algorithm, you said.
Exactly, because of the AKS algorithm, but we'll need some more connections. Maybe everybody has to see that, right? Why this AKS algorithm just implies, yeah, this algorithm. Why existence of this algorithm tells you that it is an NP. We will come to that. But as of now, we haven't discussed this explicitly, and this is the picture we have based on the current discussion. We have just considered this combination, and we know that it is there, it is in co-NP, and this combination tells you that it is in NP. You can think about these two cases. I don't think we'll have time today to discuss, but yeah, now I'll come to that question. Somebody asked about this A case, and
Uh,
so suppose, yeah, a question. Yes.
yes, ma'am. Ma'am, what is co-NP again?
Okay. So co-NP is a set of problems, decision problems for which no claim can be verified in polynomial time.
Okay. Thank you.
Okay. So now we are looking at a problem. Let's say Q is a decision problem. Okay. I'm just giving it some name, Q. Okay. Suppose I tell you that Q is in P class. What does that mean? Q can be solved in polynomial time. Okay. Then can I conclude that Q is in NP class? If I tell you that the problem can be solved in polynomial time, does it imply that the problem, yes claim for that problem can also be verified in polynomial time?
Well, one way
No.
to verify solving.
One way to verify solving, right? Everybody sees that.
Yes.
What we can do is we know how to solve it in polynomial time, so just solve it. Now once you solve it, you know the answer, you know the correct answer for the problem. So whatever is the claim, you can just match the claims. I mean the claim is saying yes, and whether you really got yes, then you can verify the claim. I'm not saying here, so here we are not talking about a certificate, right? We don't even if somebody gives the certificate, it doesn't matter to us because we have solved it. It's basically, let's go back to that earlier scenario, right? You and your friend are solving, sitting next to each other. Your friend comes to you, and you just don't hear to that person, and you are just solving it yourself. And finally, you arrive at an answer, and now you don't even need their certificate because you know the answer. So whether they are making a correct claim or not about yes being the answer, you yourself know it because you have solved it. So because you have this polynomial time algorithm for Q, the verification is also possible in polynomial time. For the yes, in fact, also for the no case, because you know the answer itself. So everybody sees this, that if the problem happens to be solvable in polynomial time, then the verification is also doable in polynomial time, both ways, yes as well as no.
Yes, ma'am.
Okay, now the next question will be, is the other way around true? Which is what we also started initially, right? If you can verify something easily, can you also solve it easily? So that's what we will be doing next. But is this part clear? And this will also let me draw a nice Venn diagram, right? So let me draw this mini complexity books and all, they will have this kind of a nice diagram. Let's see if I can draw these circles. Okay, so let's say this is P. This is a set of problems which can be solved in polynomial time. So I just said that if it is in P, it is also in NP, which means I should be able to draw something like this if it goes well as a circle. Wait. Okay, something like this. Okay, leave it. So this is NP. Everybody agrees to this because of this. If it is in P, then it is also in NP. And we also know that if it is in P, then it is in co-NP. That means this P has to be also a subset of co-NP. Right? This is just a pictorial representation of what we just said. If the problem is in P, every problem which is solvable in polynomial time, its yes verification can also be done in polynomial time. So this P set becomes a subset of NP, and its no verification can also be done in polynomial time. So the P set becomes a subset of co-NP also. So in general, P is a subset of NP intersection co-NP. Everybody sees this based on the discussion so far?
Yes, ma'am.
Yes,
Yes, ma'am.
Okay. So in terms, like in simple terms, if you want to write, if a problem can be solved easily, where easily actually here means polynomial time complexity, then its verification both ways can be done in polynomial time. Okay, I'm again talking about easily here because it will help us maybe in the next part. Okay, so the coordinators, it's already 5:40. Okay, so you can tell me if I have to stop, and then we will see. So please tell me, okay. Uh, I probably need another half an hour. I'm not sure, but yeah, we can stop if you want. Uh, okay. Okay, so now the next question is, let's look at just these two circles for now. We'll skip the ONP part for now. Let's look at these two circles. Okay, so this is just a part of this diagram. I'm just ignoring this co-NP part. Okay, so P is a subset of NP. Okay, so somebody asked this, right? Somebody was mentioning this, that if I know that the problem is here, let's say Q is here, that means, let me write it here. Suppose Q is in NP. That means Q's yes verification can be done in polynomial time. Then is it also true that it can be solved in polynomial time?
Not always.
Not always. Okay, this also relates to somebody else's question, maybe the same person, I'm not sure. Somebody asked this, right, that are there problems for which only exponential time algorithms are known so far and there are no polynomial time algorithms? Okay,
Yes, I
so
only asked it.
yeah, okay, so we'll come to both these now. Okay, in this discussion we will
uh, are
hopefully
there
answer
any
both these
proved
things.
problems that there are no polynomial?
Are there any?
Like, are there any proof? Like, is there a problem that has a proof that there is no
Yeah,
polynomial time solution?
very nice question. Let me discuss. Let me just wait for 5-10 minutes maybe. Okay, and all three questions will be answered,
I'm
I think.
ready to wait, but I also want to add a fourth question. How do you even
Yeah.
begin to prove that something is not
Okay.
solvable in a fixed complexity?
Okay. Sure. So we'll discuss that also. Yeah. So that was not the part of the agenda, but yeah, it's a very nice question. So, and I think that will give you like more complete picture. Okay. So let's do it one by one. So suppose Q is in NP, then what are the two possibilities with respect to P? Q can be in P or Q can maybe outside P, right? So there are two possibilities. Maybe I will use a color here so that I can easily. So if Q is not in P, I will put Q here. It is in NP but not in P. And in the other case here, in this case, I will put it in the inner set here. Okay, maybe green is not a good idea. Okay, so here. Okay, these are the two possible cases given that Q is in NP, right? Okay, so suppose for every Q, okay, suppose every problem in NP is also P, then what will happen if every problem is in NP? If this is always true, if for every Q, okay, so this is for all symbol, if for every problem Q in NP, if we say that Q is also in P, then what can you conclude with respect to these two sets?
I mean,
They are
P.
equal.
That these two are the same set.
They two collapse into one circle, right? So then you conclude that P and NP are the same things. Okay. Now, if there exists a Q of this type, this orange side, right, which is in NP, but Q is not in P, then you can conclude that P is a proper subset of NP. And basically, it also means that P and NP are not the same. Okay. So now we are slowly coming to this question, P versus NP or P equal to NP question mark, right? That question. So you see, what do we mean by this now, right? If we can show such a problem, if we can show, if we can show this, if we can prove this, that no matter which NP problem you consider, it is also in P. Okay, it's not done right now. It's not proved right now by anybody. But suppose somebody does that, then the conclusion will be P and NP are same. Okay, if somebody comes up with a problem, a concrete problem, so prime is a concrete problem, for instance, right? So somebody comes up with a particular Q, and they show that, see, Q is in NP, but Q is not in P. That also needs a proof. Somebody just asked this, right? Are there proofs that there is no polynomial time algorithm? Yes, you need a proof. But suppose somebody comes up with this a particular problem Q, they prove that it is in NP, and they prove that it can never admit a polynomial time algorithm. Then that Q has to remain here, which means that we are able to conclude that P and NP are not the same. And the question is unsolved. This question is unsolved because none of these have been done so far. So we don't know whether P is equal to NP or not. This is unsolved right now. That
Wait,
means,
so what is the essence of the question? Like when we were doing the prime question, didn't we just just say that if we, I mean, so it's not proven, and we don't know for any problem existing that if the verification process takes this much time, then we are sure about the solving process. But what if,
yes,
let's say, a question is proven that okay, if the verification process takes polynomial time, then the solving process will also take polynomial time. How will that
okay.
affect how will that affect these computations and all? Will they grow exponentially faster? Like what will happen with that?
Okay, so what you are saying is if I am able to show this, right? If verification can be done, then also solving can be done in polynomial
Yes, yes,
time.
yes.
But we have to show it for every problem, okay? Not just one problem.
No, I mean in a
Because,
hypothetical universe, let's say someone just gives a proof like
oh,
yes, this is
okay.
possible. Then how will that impact computation? Like will it grow
Oh,
very
yeah.
fast?
Yes, that means everything can be. I mean, everything in NP can also be solved in polynomial time. So maybe I should talk about the significance of this question. Maybe that will answer your question. If
Yes, I
they
think my
happen to be
question
equal,
is the same
right?
as
If they
significant.
happen, yeah, if they happen to be equal, then what will be the significance or what will be
If
the
they
impact,
happen to
right?
be equal, there will be a like major blow, right? The modern cryptography, SHA-256 depends
Correct.
completely on it.
I was about to say that as a first thing. Yes. So, yeah, some of you probably know that. So, the cryptography is one of the fields which heavily uses this assumption that, okay, so there is this widely known, or I would say widely believed assumption that P is not equal to N. Okay, that means there are problems like this which are verifiable in polynomial time, but they are not solvable in polynomial time. This is an assumption. Okay, this is a belief, this is an assumption, because even to have that you need to have a concrete problem, which we don't have right now. But because of this assumption, I mean, this assumption is heavily used in current cryptographic systems. So there, what we say is, whenever we are encrypting something, sending it across a network, let's say, uh, the key, right? I mean, if you have a key, you can decrypt it. But if you don't have a key, you have to try out combinations, and trying out combinations. And I mean, in a very simple terms, okay, this is not a, also I'm not not an expert in cryptography, but at a high level, what it means is, for decryption without a key, you will have to solve, which it is equivalent to solving a problem which is of this category, that it is in NP, its verification can be done in polynomial time, but its solving cannot be done in polynomial time. And because we have assumed that P and NP are not the same, because of this, such problem cannot be solved easily. And that's why, I mean, that is a basic assumption under, like somebody said, a SHA, right? Many cryptographic systems have this assumption currently. That is one way to look at it. The other way is many practical problems. Okay, so there are these fields like biology or even logistics, operations research. Maybe you have heard of this traveling salesperson problem or some genome sequencing problem. Many of such problems that come from different fields, not necessarily from computer science domain or number theory, they turn out to be something called NP complete, which I have planned to cover, but let's see. So NP complete are the hardest problems in this class. Okay, maybe I will talk about it in like 5 minutes if possible, and then complete this discussion on significance, because otherwise it will be not clear. It will not be clear what is NP complete. So suppose there is a problem Q, a decision problem. In fact, I will also say that Q is in NP. Suppose this is known. This is given. So Q is an NP problem. So its verification, yes, verification can be done in polynomial time. Now let's imagine this picture, that this is NP class and there is this Q here. Now you pick any problem in NP, let's say T1. Okay. Suppose you somehow show this, that if I can solve Q, then I can solve T1 also. Okay. So this is called reduction. I may not get a time to go through this in detail, but at simplicity, what is reduction? So let's say you want to do exponentiation, x to the power y. Okay. You can write this as x multiplied with itself y times. Okay, so exponentiation is reduced to multiplication here. If you know how to do multiplication, then you know how to do exponentiation. Okay, at a very simple, as a very simple example, we can think of this like those who have done programming. You can think of this like you have written a function which gives you a product, a multiplication, and then you can definitely implement exponentiation using that function. So you are reducing the problem of finding exponent, x to the power y, to the problem of doing multiplication. So basically what you will do is, let's say I want to do 19 to the power 5, then I'm doing 4 multiplications basically. I'm doing this multiplication, to that I'm doing, to that I'm multiplying by 19, then to that I'm multiplying by 19, third time and fourth time. So I'm reducing this problem, exponentiation, to 4 multiplications. So likewise, think about this. If T1 is a problem, which is NP, Q is a problem, which is NP, and I somehow reduce T1 to Q. Okay, so we really don't have time to, I mean, I was trying to take some examples of reduction, we'll see, but think of it in a more abstract sense, like T1 is also in NP, Q is also in NP, and I can somehow reduce T1 to Q. That means if somebody solves Q in polynomial time, then this process I design in such a way that it is polynomial time. So I can take T1, I can make this process, the reduction process, in polynomial time. Then I get Q. Now Q is also solved in polynomial time. What does that mean for T, T1?
That is also solved in
That's
polynomial time.
also
Even is
polynomial.
Correct?
also in polynomial.
Right? So this is called so this is, let's say, called polynomial time reduction. This arrow, right? This arrow that I have drawn, it stands for polynomial time reduction, which is very similar to this reduction, but here it's a very simple example, exponentiation multiplication. Here, this T1 could be from graph theory, Q could be from number theory. All such combinations can exist, but both are NP. And Q is a special problem. So let's say there is another T2, which is in NP. That also suppose you can reduce to Q1. Again, T2 could be something else, graph theory or whatever, some domain, biology, whatever. T3 is another problem. That is also NP, but you can do this. And not just T1, T2, T3, no matter which problem you look at NP, you can always reduce it to Q. So
So we
suppose,
just need to like find a polynomial algorithm for reduction, and then we are absolutely done for this entire set.
yes. So suppose for every problem in NP, so for every problem, let's call it T in the NP class, suppose you can reduce T to Q. Okay, so this means T is reduced polynomial time. Because the reduction itself, if it takes exponential time, then we can't get the entire algorithm for T in polynomial time. So T is polynomial time reduced to Q. So this arrow means this polynomial time reduction. Suppose this holds and okay, suppose this holds, then in fact I would say P is called an NP complete problem. I wanted to define that first. So this is called an NP complete problem. Okay, so I have jumped a bit here. I mean, I have not defined a few other classes. So if Q is in if Q is in NP, okay, and every other problem in NP reduces to Q. Every other, okay, not some of them. Every problem in NP you can reduce to Q in polynomial time. Then this is called as an NP complete problem. Now suppose just now somebody said, right, suppose Q becomes P. I mean, suppose Q is solvable in polynomial time now. Then what does that mean?
Then
And all the others are also solvable.
Everything is
So in other words, NP is P, right? NP
Yes.
collapses to P, right?
Yes.
And that's why these NP complete problems are in some sense very powerful, because when you solve them, if somebody comes up with a polynomial time algorithm for Q, Q is a hypothetical problem. There are examples which I can tell, but let's say some hypothetical problem for which you can find out a polynomial time algorithm, then it not only solves Q, it solves everything in NP. So in some sense, Q is a very, very powerful problem because it has this capability of solving the entire set of entire set NP, all the problems in NP. Given that the reduction is polynomial, right? Because when we do this reduction, the running time for T1 will be the time required for reduction plus solving Q. So both have to be polynomial time. Just having Q polynomial time is not helpful. The reduction should also be in polynomial time. But right, and in fact, such problems exist. You can show that any problem in NP reduces to them. So some examples of those are, I'll just mention, maybe we'll stop in like 5-10 minutes, but I'll just mention some examples of NP complete problems. And in fact, yes, if you can solve one of them in polynomial time, then yes, you will end up in showing P equal to NP. So examples. So let me just write down some examples. I may not explain those in detail. There is this decision question on vertex cover problem. Vertex cover is a graph problem. Has anybody heard of this problem? Independent set is another problem in graphs.
Vertex cover is the one where we have to choose a bunch of vertices so that all the edges are covered, right?
Correct. Yeah, yeah. Vertex cover is the one where you choose a subset of vertices such that every edge is covered. Covered meaning every edge will have one of the two endpoints or both, maybe in that chosen subset. And
and
the
independence.
decision, yeah. So I'll just talk about decision thing here. So the decision question here is that think about a graph. So maybe I'll take a quick example. I'll show both. Please stop me, coordinators. Please stop me when you think that it's time to stop. Okay. Uh, we we planned for 2 hours, so yeah, please stop me. So let's look at this simple example. Let me give some numbering: 1, 2, 3, 4, 5, 6. Okay, so now if I talk about vertex cover, let's say I just take 2 and 5. So is 2 and 5 a vertex cover? So it's not, right, because it's not a vertex
No,
cover.
because the 3 4
Because
edge is not
yeah,
covered.
because 3 4 edge is not covered, 4 6 is not covered, 1 3 is not covered. A lot of edges remain uncovered. So 2 5 is not a vertex cover. But this particular graph, if you consider all the sets, sorry, all the vertices, everything, is that a vertex cover? Trivially,
Yes,
Yes,
mostly.
trivially,
certainly.
yes, right?
Yes.
Trivially, right? Nothing to do there much. But we want something which is minimum size. Now 2 5 is not possible. So maybe we should consider another size 2 vertex cover. Is there a size 2 vertex cover? If not, maybe size 3 is the minimum possible. Maybe size 4 is the minimum possible. So that becomes an optimization problem. You want to minimize the size of a vertex cover. And what is a decision question here? We are not looking at the optimization problem here. We are saying that I have given you a graph like this, and I have also given you an integer k.
And there exists a vertex curve with k vertices. This is the thing we have to.
Yeah, at most k vertices, because we are minimizing it, so we will put an
Fair enough.
upper bound, right? At most k, yeah. So at most k size does
If
there
we can
exist?
do less than k, then we can do k.
Yes, that is also true. Yes, if we can do less than k. But typically, the decision questions which are coming from optimization questions, they are usually upper or lower bounded. Here we will lower bounded in the maximization problem. We'll come to that. But yeah, equality is also fine. But this is like a very conventional thing. You upper bound it. You will say at most k. Now, what is an independent set? So, independent set is another like similar to vertex cover, but it's a subset of vertices such that if you pick any pair in that chosen subset, there should not be an edge between them in the original graph. Okay, so if I look at, let's say, 1, 4, 5, then it's not an independent set because there is an edge between 4 and 5. We want that in this chosen set, no pair should have an edge. So in this chosen set, 1, 4 doesn't have an edge, but 1, 5 they have, 4, 5 have. So this is not an independent set. So can you give me an example? So what about empty
Like
set?
if we
Is
choose
that an empty?
any
Just
side,
5 also
we
works,
choose
like just 1, 2, 3, 4.
Yeah, even
four,
just single vertexes works. But what about independent? What about empty set?
Yes, that also.
Empty
and
set
is it
is also like
true?
a very trivial example. Yeah,
Is
two
it
and
true that if we have a three size independent set, that's just not possible in this graph?
do we have a three size independent set? Okay, let's
That's
see.
not
Wait.
possible, it seems.
Yeah. Let's see. So everybody agrees that this single vertex becomes an independent set, right? Because there are no pairs at all to consider. Again, empty set and single vertices are like trivial cases of independent set. Is there any non-trivial independent set which is not like single vertex and empty set?
Two other.
1,4.
Okay, 1 comma 4. Great. Yeah, so there is a 2 5 also, 1 6 also, right? Yeah. So many
Basically,
of
any
them.
pair of non-adjacent vertices.
We
Yes,
cannot
correct.
find one of three because we must take one from at least one of the two triangles that are.
Right. Yeah.
So,
So, yeah.
yeah.
So somebody asked this question: can we find an independent test of size 3? But before that, let me talk about the decision version. We are given G and K, and we will say that is there an independent set of size at least K? Because we want to maximize it, so we will put a lower bound. Is there an independent set of at least 3 here? So the answer will be no. There is no size 3 independent set here. If k happens to be 3, then the answer, it's a decision question now, right? So with k equal to 3, the answer to this will be no. With k equal to 2, answer will be yes.
And so anything after three subsequently will be no.
Yes, right. Similarly here, right? When we have sorry, something smaller than k automatically is there. So
If we wanted to do the independent set decision for to find the maximum number of vertices you can have, that
yes.
would pretty much be the same as the vertex cover decision.
Yeah, I'm coming to the connection between the two. But yeah, just hold for 2 minutes maybe. Is this the definition and the example is clear? Any questions about
Yes,
the
ma'am.
notion? Okay, okay. Yeah. So now let's observe some connections. In fact, okay. But why I told about these two examples is they are NP complete problems. So what do I mean by that? Okay, so they have to be, first of all, they have to be NP. Remember, that is what we started with. Suppose Q is in NP. Okay, that is a given thing for us. If Q is in NP and everything in NP reduces to Q, right? Then it becomes NP complete. So when I say it is an NP complete problem, you have to first think about this. How will you show that this is in NP? Now you know what do I mean by NP, right? This decision question. Given a G and K, the answer to this will be yes, no. How will you verify the yes claim? What kind of witness will be required and so on? Now you cannot say here that I will solve it and then I will verify, because it's, as of now there is no polynomial time algorithm for vertex cover decision question for general graphs. There are different types of graphs for which some of which are solved, but for the general graph there is no polynomial time algorithm.
But
So
what
this
is
is
our
also
input
that
size? for this question?
Yeah, so
Because
yeah,
we
we'll
also
come to
have the
that.
graph and we have k. So
Yeah, so we are given a G. Again, think about this. You and your friend are given this graph, you are given this K value, you both are solving it independently, and then your friend comes to you and says that the answer to this is yes. Okay, we are talking about NP. The answer to this is yes. So what is he or she claiming exactly? They're claiming that there is a vertex cover of size at most K. That is their claim, basically. So what should they give you so that you are convinced?
the cover.
Some values of vertices, like a certificate.
Yes, so the certificate itself is a vertex cover, right? They should give you a set, right? Something like this, whose size is at most k. And what will you do to verify that? You will actually check,
We'll
right, that
manually check.
every edge has been
Just
covered.
check all the possible combination.
No, why do you need to consider all possible
We
combinations?
will
We are not
check all the
solving it.
edges.
Yeah.
Oh, yeah, yeah.
Okay. Yeah. We are just verifying it. Okay. Your friend has
No,
claimed
no, I
that
was
the
saying
solution.
that in the set, in the vertex cover.
Oh, you mean in this certificate?
Yeah, in the certificate.
Yeah, you don't have to consider combinations. You will look, in fact, look at every age. Like you look at 1, 3 and check whether 1 is there or 3 is there. At least one of them should be there. So you have to do a check for every age. You don't have to consider all combinations of this certificate. And that is definitely polynomial time because the size of the input itself has all the ages. Like m, if m is the number of ages of this graph, then you are doing m many steps, and every time you are checking in this set which has k size, and k cannot be more than n because it's a subset of vertex set. So then it is polynomial time. So the verification can be done in polynomial time. So it is in NP. Now think about this also offline, whether this has to be in NP, right? Because I said that it is NP complete. Okay, so this you can do, but the main thing is, can you find a connection between the two? Is there any connection?
Ma'am, I think I have
So
connection.
yeah,
So like
yeah,
basically,
you were saying something. Yeah.
yes, ma'am. So basically, if you could find the maximum, like I mean, if you find the like smallest possible value for the vertex cover decision,
Mhm.
then you just take like all the vertices which you did not use,
Mhm.
and then that would give you the maximum for the independent set decision.
Yes, right. That is correct. So let me write this down. G has. I will come back to that, but let me write this down. What he said. So G has a vertex cover of size at most k. It implies that the same G, the same graph has an independent set of size at least n minus k, where n is actually the number of vertices in the graph. And it's the other way around also. It's if and only if, both ways. So I think that is what you said, right?
Yeah, yes, ma'am.
Okay. So does everybody see this? So let's actually concretely find out what is the minimum size vertex cover here. We have written 2, but what is the solution here? Let's not talk about decision question. You tell me the minimum size vertex cover here. It's not size 2. Maybe there is another set of size 2 which is a vertex cover. Or if not, maybe there is a size 3 vertex cover. If not, maybe there is a
Minimum
size 4 vertex
size.
cover. So what about this? 1, 2, 1, 2, 4, 5. Is this a vertex cover?
Yeah, I think 4 is the minimum.
4 is the minimum. You mean size, right? Size 4 is the
Yeah,
minimum.
yes.
Yes, that
Okay,
seems to be
so everybody says this is a vertex cover and this is also the minimum
Yes.
one, minimum size one. You cannot have a size 3 vertex cover. You can, yeah, I mean, because we don't know polynomial time algorithm, all you can do is try out different subsets as of now. There are some observations you can apply, but in general, I mean, there's this triangle and all that. But in general, all that you have to do is brute force, some intelligent brute force maybe. And what is the maximum independent set in this graph? So 1, 4 is 1, right? But is
Who
there
is?
1, 4 is, but is there a size 3 independent set?
No, there cannot be.
No, there
There
cannot be.
cannot be, right? In fact, that's what I've written here, right? That n minus k and k, they have to sum up to n. So if you have found a vertex cover, minimum vertex cover of size 4, and given that it has 6 vertices, you cannot have an independent set of size larger than 2. So in fact, this itself is your optimal solution for the largest size here. Okay, and that is not by coincidence. It is by definition of vertex cover and independent set, right? If you choose this as to your vertex cover, 1, 2, 4, 5, whatever vertex cover you have picked, Then look at the rest of the vertices. If they had an edge, if between any pair there was an edge, then who is covering that edge? Neither 3 is there in the vertex cover nor 6. So it is not possible that they have an edge between them, any pair in the remaining vertices. Which means if you have chosen a vertex cover of size k, the rest of the vertices have to form an independent set. And the other way around also.
Ma'am, I just have one question.
Yeah.
So basically, how do we even prove that they are NP complete problems? Like, how are we
Yeah,
supposed
yeah,
to
I'll
do
come to
that?
that. I'll come to that. Yeah. So is this part clear that they are related by this claim? Let me complete a discussion on these two problems, then we will answer the other things. Coordinators, please tell me when I have to stop. Okay. Is this connection clear between the two? And this also gives us a reduction. Okay, think about this now. How will you reduce? Think about this. How will you reduce decision problem of vertex cover to independent set and the other way around? Because of this connection, it's possible to do this in polynomial time. Okay, but this is a bit of like it will need some discussion. You can think about this offline. I'll come to other questions now. But these are two examples of NP complete problems. And as I said, the NP complete problems are like most powerful in the sense that when you solve them in polynomial time, not just they are solved, the entire NP set gets solved. So it's really, and I mean, it's really a very kind of a crucial part in this, that if you solve any one NP complete problem, there are many of them, not just these two. There are many of them. If you solve any one of them, then you in fact prove this unsolved question. You are done with that. But so far, nobody has been able to show that any of such NP complete problems have polynomial time algorithm. Now that comes that there comes another question: can we show that, for example, vertex cover decision will never admit a polynomial time algorithm? How do we show that particular problem will not have a polynomial time algorithm? That's a different aspect of this, right? So how to show? How do we show that, let's say, some q, which is, let's say, NP complete, not just NP, is does not admit it at all? Does not. It's not that it's our limitation, or maybe it will need 10 more years. It's not like that. Maybe it will never admit. Does not admit a polynomial time. How will you show that? That is another question somebody had asked, and it's also related to this discussion. Yeah. So this particular question is there is no single answer. I mean, if we knew this, if we knew that there is a systematic mechanical procedure, then possibly it was solved by now. But it's not true that there is, a standard mechanical procedure like that. But I will tell you a very related kind of a thing. Some of you mentioned this part, right? The sorting cannot be done. So the best you can do, right? The best sorting algorithm is n log n, given that you are restricted to the comparison based sorting. Remember, somebody said this, comparison based
Yes.
sorting. Any sorting algorithm which must use comparisons, it cannot beat n log n. That means you have to spend n log n as a lower bound. You cannot go below that. You cannot have something which is growing slower than n log n. So this is called lower bound result in some sense, because you are saying that something cannot be beaten and you cannot make it faster. So this is like a lower bound result. You need at least in log n. You cannot beat that. You cannot go below that. Okay. So in some sense, we are looking for lower bound results here. We already know that vertex OR can be done in exponential time. Can we beat that and go slower? Go to the polynomial time. Okay. So if anybody remembers or anybody has learned why this is true, how do you show this? You may not have, but I'm just asking. I mean, do you know how do we show this, that it is indeed the best possible for comparison based sorting? So there is a proof for that. It's not just that nobody has been able to find anything better, so we say this is best. It is not like that.
I know
There is a
there was.
theoretical proof.
I don't know the proof. I know there was some there was a decision tree approach to.
Right, right. Yeah. No, that is correct. I mean, decision tree, and then you will do the analysis of that. Yes,
Yes.
that is correct. But you see, there is a proof. It's not that okay, nobody has been able to find anything better than n log n, so let's say that it is the best. It is not like that, right? There is a proof that this is indeed the best possible. You cannot beat this as long as you are restricted to comparison based sorting. There are other sorting algorithms which do not need comparison, but you also need some kind of a restriction on data, in that case what data you are sorting, and then you can beat n log n and you can go linear time, like just n and so on. Again, that is not the topic of this discussion, but uh, of course you will not be restricted to comparison there, and you can do other things based on the data, so you can beat that. So it needs a proof, and this proof is completely, I would say, given that it's a sorting problem, given that it is a comparison based restriction, the proof is very tailored to kind of this setting. So there is no generic method where you show this. Okay, there is no generic method where you show this. How do you show this? But yes, you need a proof. If you want to show the other way around, that p is not equal to np, then you have to show that, pick some problem, okay, and then you show that some of these one of these problems, and show that that will never admit a polynomial time algorithm. Okay, how does that help showing p is not equal to np? Suppose q is np complete. Okay, and suppose this is proven, maybe few years down the line, suppose it is proved that q is not in p. How does that tell you that p and np are not the same? Because it just says that q is not in p, right? Remember, if q goes in p, so what we said earlier is different, right? We said that this is np, this is p, correct? So what we said is q is this special problem, very, very powerful problem. Everything in np reduces to q, like this. In fact, all the problems in p also reduce to q because p is a subset of np. Okay, but as such, solving q doesn't help these problems because they are already polynomial time. Okay, but everything outside p reduces to q. So if I take q inside, everything collapses. That's what we mean, right? Because if q becomes here as a part of p, then everything collapses because everything goes in that inner circle. This is fine. But if I show that q stays there, okay, this means that I am showing that q stays in the outer circle. It doesn't go in the inner circle. How does that help me show n p is not equal to, this is p, this is np. If I show that q stays here, q never goes there. Maybe there are other ways, right? Maybe you can put them inside with some other method, not via q. Why can't that happen?
But like Q itself won't be P, so
Q
that's
itself won't be p, but see, solving t1, this was one way, right? This was one of
right.
the ways to solve t1. Go to q, and if q happens to be in p, then automatically t becomes p. T1 becomes p.
But didn't
That
you
was
said
one way.
if there is anything in NP which is not in P, then NP is not equal to P, and Q is
Okay, so
like
you mean NP is not equal to P because you showed the existence, right?
yeah, like Q itself is the thing which is
Yeah.
not
So you
yeah
showed something which is in the difference. You showed a problem Q, which is in the difference of this, right? NP versus P. And because the
yeah.
difference
Maybe
is
every other
non-empty,
problem could be in P, but Q itself is not in P.
correct. So it doesn't matter, right? I mean, that is what I'm trying to highlight, that these problems can have other ways. Maybe they will belong to P later on. That's fine. But as long as you show that here is a Q and I prove, now, how do I prove? Frankly speaking, I also don't know. That is the main crux of this. How do you show this thing? But just like this proof, right? This is kind of a similar proof, lower bound, that you cannot beat n log n. And here you have to show that you cannot beat exponential. That is what you want to show here. So suppose somebody shows that q, for q you cannot beat exponential, then q stays there. And where does q stay? Q stays in this difference. That means this difference is not empty. Somebody is there. That means p and np cannot be same. So both ways it is a challenge right now. How to show that any NP incomplete problem cannot be, you cannot beat exponential time for those. That itself needs a proof. That is not been nobody has been able to do that as of now. And on the other hand, if you show that you take some NP incomplete problem and design a polynomial time algorithm, that will pull everything into P, but that also nobody has been able to do for any of the NP complete problems. And there are hundreds of them, at least. I mean, I know a few, maybe 20, but yeah, there are many of them, and they come from different domains: graph theory, number theory, and logistics, biology, set theory, yeah, lot of things, lot of domains. So in that sense, yeah, it's a very theoretically itself, it is a very challenging question, and we were discussing about the significance, and that's how I diverted to this NP completeness. Uh, so where was I discussing? So I think here cryptography and all that we're discussing, right? Mm. So I was talking about cryptography, which has this assumption that this widely believed assumption, right, that P is not equal to NP, and if somebody shows that some NP complete problem can be solved in polynomial time, then these two circles, these two sets collapse into one, and then P becomes NP, and then those systems where they have this assumption, they can be broken now. That is one aspect of that. The other aspect I was telling is that in the logistics and operation research and many other fields, biology, many problems have been considered, and they are very important for the research in that particular domain, but they turn out to be NP complete. So traveling salesperson, for instance, is another example. Traveling salesperson, which comes very often in OR, and its variants actually is traveling salesperson problem. So this is also NP complete. And this is closely related with Hamiltonian cycle, which you know possibly, Hamiltonian cycle in the graph. So it's very closely related to that. Uh, yeah, so that is also NP complete, and again the same thing. We don't know how to solve it in polynomial time because nobody has come up with an algorithm yet. But does that mean it can never be solved? We don't know, because that also needs a proof, and we don't know both ways. So that is the status for all these NP complete problems. And other than this, one other thing which you can also think of this is this. Suppose you are studying a theorem. Okay, suppose in your curriculum in your school you are studying a theorem. So most of the theorems that you will study, right, in your textbook, they are done by somebody earlier, right? Somebody has proved them, and what you are doing is you are trying to understand the proof, and implicitly you are actually doing a verification of that proof, right? When you see the theorem and a proof written in your textbook, or if the teacher is teaching you that, then all you are basically doing implicitly is the verification of the proof which already exists, right? You may reproduce it in the exam, you may add your own things, you may come up with a different way or simplify it, that is fine. But typically what we do when we study existing theorems is we are verifying the existing proof, and maybe we are able to reproduce it in the exam or whenever asked. Now think about proving the theorems. Okay, so this is another implication which I think it's a bit I mean, it's not like domain specific, mathematical proofs. Okay, so coming up with a proof versus verifying somebody's proof. So you want to come up with a proof yourself versus somebody has verified, somebody has proved it. Maybe some mathematician, Pythagoras. I mean, some proof that you may have studied in your curriculum, or maybe your friend has proved it. Okay, whoever has proved it. Now you are just verifying it. So intuitively, it seems like verification seems to be a much simpler job, because now you have the entire proof with you. All you are doing is, does step one make sense? Is it a valid assumption? Is it in the given part, or are you like making it up? You just have to verify that. Once that is verified, go to the second step. Does it logically follow from the first step? Yes. Go to the next step, and you can verify it. But think about coming it up with like on your own, coming up with a proof. So there are these conjectures, right? For instance, there is this Goldbach conjecture, if you have heard of that. uh, Goldbach's conjecture. So it's a conjecture. So far nobody has proved that, and so it's a number theory conjecture. I think it says that anybody knows Goldbach conjecture. So every even which is greater than 2 is a sum of
Sum
2
of
primes.
primes.
Yeah, it is a sum of 2 primes. So for instance, 8 is 5 plus 3, right? So this is true for every number, every even number greater than 2. That is what is a conjecture. Why is that a conjecture? Because it's not proved yet. But even computationally, people have tried different even numbers to a very large scale, like very huge numbers, and they have found primes with sum up to that number. So no counter example has been found so far. So it's a conjecture, but you can't call it a theorem right now because it's not been proved. So think about proving this, okay, versus somebody comes up with a proof and you are verifying it. So inherently, it seems like given a proof, verifying it step by step seems much simpler than coming up with a proof yourself, because you don't know which kind of axiom will be used. How do you combine different things that are already proved? In which way you want to combine? Maybe you want to take the implication, or maybe you want to consider the contrapositive. You don't know, right? You'll have to try different possibilities. So just like the Sudoku, it seems like solving is much more tedious than verifying it. So this is something which I find like quite related with NP. So when we do this P versus NP question, that uh, is verifying an existing proof is easy. So is solving also as easy as verifying a proof? So this is at least my take on this. I mean, this is nothing specific to any domain or any. This is more like a theoretical question, like coming up with proof versus verifying an existing proof. Do they have the same complexity? Verification seems to be much simpler, but this is very, you can map it with that P versus NP kind of a thing, where solving is like, if you can solve it easily, then it becomes P, whereas verification seems to be in NP because you can, it's much easier than solving it. Yeah, so that is kind of a theoretical aspect to that also. And practically, I said that cryptography and other many fields will have different implications based on the result, based on the answer to this question, P versus NP. Yeah, so that is what I plan to cover. I mean, I wanted to consider the binary search, given that you already know that problem, but that's okay. I think you got a fair enough understanding of complexity. So yeah, sorry, it's been like 2.5 hours already. Please please ask any questions if you have, if you haven't covered. Four color theorem. Okay, I'll just read through the chat meanwhile. Oh, sorry, I didn't see this message that somebody is asking to. Uh, uh, I don't know what does that mean, but yeah, I think somebody wanted me to complete the class. Sorry, I didn't see the message.
Ma'am, is
Uh,
max TSP solved for convex hull?
for convex hull, what is that restriction? Convex hull meaning?
If
Your
the points
endpoints
are on
are.
a convex polygon.
I'm not sure. I'll have to see. In general, it is NP. I mean, the decision version of that is NP complete, but convex hull, I don't know. I don't remember reading about it actually. We'll have to check. For vertex cover, I can tell you that on bipartite graphs, it is not NP complete. It is, I mean, it is NP, it is NP, but it is also in polynomial time. On bipartite graphs, if the graph is bipartite, then you can find out the minimum vertex cover in polynomial time.
Okay.
Yeah. Yeah, so here this G, this one is not bipartite, by the way. You have this triangle. I hope you know bipartite graphs. But anyway, even if you don't know, what I mean to say here is there are specific graphs on which the problems are polynomial time, but the general problem is not known to be known to admit polynomial time algorithm. Okay, I don't see any specific question in the chat which we haven't discussed. So please let me know in case I've missed something.
In case there are no more questions, we can stop. Thank you, ma'am, for the
Yeah,
class. It was
okay. And thank you. It
very
was a bit
interesting.
delayed, and yeah, sorry, it took a little longer. Uh,
Oh,
okay,
no,
thanks.
really, no problem. It's some very cool stuff you did. I had a great time. I think everyone else
Okay,
had.
thank you. Yeah, thanks. Okay, then disconnect.